Hi there, welcome in this new video presenting some of the nice achievements obtained by students during the Advanced Control on Embedded Systems lab. This teaching activity is part of the teaching unit Advanced Control 2 and is co-supervised by my colleague Sébastien van Koenberg and by myself. Like previous years, students have received either an EduMIP robot kit or a Balboa robot kit. Both kits come with breadboard, connecting cables and a set of ultrasonic and infrared sensors. As you can see, the Balboa robot kit comes also with a Raspberry Pi 4 computer. The EduMIP robot is equipped with a BeagleBone Blue embedded board for Linux-based robotics and control. The Balboa robot comes with an Arduino-compatible microcontroller. This year we had 8 teams of 2 students taking up team-related problems. 4 teams working on the EduMIP robot and 4 teams working with the Balboa robot. In this video we'll present 5 out of 8 team results, 4 based on the Balboa and 1 based on the EduMIP robot. As you can see, there are 8 laboratories. 4 of them are dedicated to learning, that is to implement a state space controller with the observer, and the 4 remaining labs are development sessions that are dedicated to the team problem, and their students work in relative autonomy. Let us now focus on some novelties. This year we have imposed a customer-supplier relationship with a customer that wants a state-of-the-art solution with some innovative aspects. The idea is that the customer and the supplier must agree on the specification, deliverables and so on. What is the state of the art is really what was done in the previous years, and of course the customer wants something new on top. Once specification is compulsory, the customer imposes that the final solution should implement a state space controller with a state observer. Before we start the presentation of the projects, let us have a look at the evaluation criteria. As you can see, there are 4 of them with equal weight. The first criterion is continuous evaluation. This has to do with soft skills, project management and so on. And one very important sub-criterion is the care for the equipment. The team is also evaluated based on their portfolio, which is meant to document the solution in English. This is also new since this year, and it has to be in full detail. The next evaluation criterion is the YouTube quality video that presents the technical solution at a high level. This video is meant to sell the final solution to the customer. Since this year, this video has also to be in English. Finally, a FAT or factory acceptance test evaluates whether the solution meets all the specifications that have been agreed upon. Without further ado, let us now start with the presentation of the projects. What I will do is use the presentations that have been made by each team for the video with possibly some minor modifications. Let us start with Balboa Team 1, composed of Whale Encourie and Keanu Bush. They have taken up the base stage problem. The robot is asked to return to a base station, like it is the case, for example, for a lawn mower. It is the first time that this team problem has been selected, so in itself that is already an originality. And in addition to the usual modifications to the mobile robot, they have to develop a base station. This is the base station PCB. The base station is Arduino based and composed of up to 4 infrared emitters emitting infrared light in 4 different directions. In the project, only 3 infrared emitters were used. This is the infrared transmitter that was used in the base station. As you can see, the infrared signal is emitted at 38 kHz. The Arduino ER remote library was used to control the ER sensors. However, using this library, it is only possible to control 1 sensor at a time, which is of course problematic for the team problem. This is the solution that was finally implemented to circumvent the problem using only 1 digital Arduino output. As you can see, 4 transistors have been used here to activate the ER emitters in sequence using the digital pins 6 to 9. Based on the different emitted command signals, The robot will be able to distinguish between the different ER emitters. As you can see, the mobile robot is equipped with the ultrasonic distance sensor that is standard in the robot kit, and with a infrared receiver. This is the infrared receiver that equips the robot. It is used, of course, to detect the infrared light that is emitted by the base. It has a detection range in theory of 18 meters, in practice a lot less. The ultrasonic sensor is used to detect if there is an obstacle and to know if the robot has arrived at the base. In the following video that has been accelerated by a factor 2, you can observe the return to base of the mobile robot. The algorithm is as follows. The robot turns around until an infrared signal is detected. Once a signal is detected, the robot drives in the direction of the signal. If the infrared signal is lost, the whole operation repeats itself. The process stops once the ultrasonic sensor detects an obstacle at a certain distance. For simplicity, it is assumed here that there are no obstacles other than the base station. The next project is by Team Balboa 2 and is composed of Florian Disneux and Mohamed Boutard. Team Balboa 2 have decided to develop a SLAM robot. SLAM stands for Simultaneous Localization and Mapping. The goal of the robot is then to be able to construct a map of an unknown environment. In the picture you can recognize the final version of the Balboa robot. 2 laser sensors are mounted on the platform that can be moved by a servo motor. Additional computer power is provided by the Raspberry Pi board that is nicely integrated on the Balboa robot using a 3D printed mount. A buck converter is used to reduce the battery power from the Balboa robot to the 5 volts that is necessary to power the Raspberry Pi board. The originalities of the project are, among many, the use of the Raspberry Pi, the nice mechanical assembly using 3D printed parts, and the real-time construction of a map of the environment. Here are the main objectives of the project. So move the platform with the laser sensors using a servo motor, acquire the laser data and send them to the laptop with MQTT. Make sure that the laptop user inputs are sent to the robot as set points. Compute the robot position in Cartesian coordinates. This is what is meant by basic odometry, and then send the data to the laptop via the Raspberry Pi. And finally, display the map of the environment in real time. The laser sensor that is used in this project is shown on the screen. It uses invisible eye-safe laser pulses, and the distance is measured using the time of flight principle. In the following electrical scheme, you can see that the Raspberry Pi is powered via a buck converter directly connected to the battery, and this is because the 5-volt supply of the Balboa is not powerful enough. You can also see how the 2 laser sensors are connected to the Raspberry Pi, and you can see that the data exchange occurs via the I2C protocol. The servo motor is powered via the 5-volt power supply of the Balboa, but it is controlled through the Raspberry Pi. And finally, the Balboa and the Raspberry Pi are connected via a USB cable for data transfer. In the following slide, you see a summary on communication. As said before, the Raspberry Pi and the laser sensors communicate via the I2C protocol. The Balboa robot and Raspberry Pi communicate via serial communication. The Balboa robot sends odometry data to the Raspberry Pi, and the Raspberry Pi sends set points for the balancing algorithm to the Balboa robot. The Raspberry Pi and the laptop communicate via MQTT. An MQTT broker is running on the Raspberry Pi. The Raspberry Pi sends sensor information and odometry data to the laptop, whereas the laptop sends set points for the balancing algorithm to the Raspberry Pi. The Balboa C++ code was extended using a number of functions that have to do with odometry and transferring set points. The LiDAR functionality and the MQTT communication was programmed on the Raspberry Pi using Python code. The LiDAR to grid map conversion, the visualization of the robot pose, and finally the real-time visualization of the environment map was programmed on the laptop also using Python. The following video shows the real-time construction of the environment map. Note that the video was again accelerated by a factor of 2. Notice on the lower left part of the screen that the robot is controlled from the laptop using keyboard inputs. Notice that you can observe some small drifts occurring in the heading angle. Attempts were made to correct for this using the Balboa magnetometer, but this proved to be difficult. Indeed, the magnetometer is influenced by the magnetic fields originating from the Balboa itself. Mehdi Azouzi and Marwan Lakrakchi form Team Balboa 3. They've considered the line tracking problem with obstacle avoidance. The main difficulty of the project was that they were forced to do obstacle avoidance using only one ultrasonic distance sensor because of I/O number limitations. For line tracking, they have used the 5-channel reflectance sensor array that is mounted below the robot. The 5 sensors are capable of identifying changes in reflectance on the ground underneath the robot. On the screen you can observe a test with the line sensor test function when the robot's first sensor is above a black line, and you can clearly observe the difference in reflectance. For obstacle avoidance, they have used the ultrasonic sensor that comes with the robot kit and that is used in many projects. A time of flight principle is used to calculate distance. The original plan was to use several ultrasonic sensors, but very soon it became clear that the 5-sensor reflectance array was using most of the I/O. As you can see over here, only pins 0 and 1 are free to connect the ultrasonic sensor, and this is indeed how it is connected. Pins 2 and 3 are not available because internally they are used for I2C communication with the inertial sensors. Without going into the details, this is the state machine based algorithm that is implemented. There are 3 main functions in this algorithm. The first function is the line detection function that steers the robot on the line when one of the sensors detects a black line. The line tracking function keeps the robot on the line based on sensor information, and it does that using a controller. The obstacle avoidance function uses distance information to get around the obstacle until the reflectance sensors detect a line. This was of course the most challenging function to write, especially using only one distance sensor. Let us have a look now at the FAT results, the factory acceptance results. First with a track with small obstacles, and then with a different track and one larger obstacle. Note that the video has been accelerated twice. Next, we'll consider the project of Moussa Hussein and Dani Progno, and this project is Balboa Colored Light Tracking. Together, Moussa and Dani form Team Balboa 4. The main novelty and also difficulty of the project is the successful commissioning of a colored light sensor. They have spent quite some time in calibrating the sensor so that it could function in different environments. These are the specifications that have been agreed with the final customer. Well, the same functionality as last year, that is, the robot must be able to follow a flashlight. But when a red light is detected, the robot should rotate. When a blue light is detected, it should reverse. And when a green light is detected, it should slow down and make a buzzer noise. For light tracking, two LDRs or light-dependent resistors were used in a voltage divider scheme. These LDRs are mounted on the left and right side of the robot. The code from last year's project was modified to implement this light tracking functionality. As said before, the novelty lies in the use of a color sensor. This color sensor contains white LEDs to illuminate the surface of an object. The intensity of the light that is reflected back can be calculated at different wavelengths. A frequency proportional to intensity is produced at the analog output that you see over here. The color sensor has an array of 64 photodiodes to transmit the different wavelengths of the detected colors. There are 16 photodiodes with a given filter for the colors blue, red and green, and the remaining 16 photodiodes do not have any specific filter. The specific filters for a given colors can be set by the digital inputs S2 and S3. The two digital inputs S0 and S1 can be used to set 4 different scales for the output frequency. Using the LDR information coming from the left and right sensors, it is possible to make sure that the robot tracks the flashlight. This is done by adjusting the speed set points for the left and right wheels. Once the color is detected, it is possible to implement color-specific commands. As you can see here, for red, turn, for green, buzzer, and for blue, reversing. Let us have a look at the factory acceptance test results. On the left side of the screen, the experiments are done with ambient light, and on the right side, they are done in a dark environment. As you can see, Musa and Danny have been quite successful in implementing a normalization procedure so that light detection is robust whatever the environment. The final project that is presented in this video is the project of Team EduMIP 4, Exit of a Maze or Exit of a Labyrinth. Team EduMIP 4 is composed of Mohamed Monir, Oussama Elmimouni and Paul Gérard. The main originality of this project is the use of a thread to compute the ultrasonic distance measurement without interfering with the balancing algorithm. If the balancing algorithm and the distance calculation are programmed sequentially, this can lead to time step overflows. At best, this degrades the balancing algorithm, but this can also lead to instability in some cases. It is the first time that this idea of running things in parallel using a thread is actually used. The main idea of the project is to exit a maze of random geometry using the EduMIP robot. As in previous years, the algorithm that was used is the so-called right-hand rule algorithm. The EduMIP follows the wall to his right. This is not optimal but easy to implement. The algorithm needs 2 ultrasonic distance sensors, one on the right, one in the front, and the algorithm was programmed using a state machine approach. In previous projects, the distance measurement was implemented sequentially with the balancing algorithm, leading to time period or time step overflows. The pragmatic solution that was then used to limit the impact of the overflow was to calculate the distance every so often, typically once every 10 samples. A much more elegant solution is to run the distance calculation in a thread that runs in parallel so that there is no influence on the balancing function. One thread was used to compute the two distances sequentially. Attempts to use two threads to compute the right and front distances in parallel were unsuccessful because the two sensors were interacting. The maze algorithm was implemented using a 5-state state machine and fuzzy-like commands like slightly right, right, strongly left, and so on. Let us take an example. State 2 corresponds to a situation where f is true, so the distance front is less than 20 centimeters. There is a wall in front, and r is true, which means that the distance to the right to the wall is less than 20 centimeters. So obviously the robot has to stop, otherwise it would bump into the wall in front, and it has to turn strongly left. Let us now have a look at the factory acceptance test results for two different labyrinths. The video has been accelerated 3 times. This concludes this year's compilation video. We want to thank all students for their efforts and motivation. If this sounds like a lot of fun, well, you should join us at Team Automation. See you next year.